So thanks a lot for the invitation. It's very nice to be here and to attend a conference in presence after more than 1.5 years. And I tried not to put too much content in this talk, so I tried to refrain myself from putting too much on the slides, so I think we can do this hopefully fairly relaxed. And if you have some questions in between, feel free to ask them. Okay, here in the room, people don't have a microphone, but I hope I will remember to repeat the question to everybody. So I'm going to talk about Fixpoint games, and this is joint work with Paolo Baldan and Tommaso Paduan from the University of Padova, and with Kristina Michalski, and she's now at the Hochschule Rhein-Waal. Okay, so this is the table of contents. And as Matthias already said, we'll now be talking about nested fixed points. So, or in other words, systems of fixed points equations. So we will start fairly easily and just talk about the case of one equation, which should be quite familiar to most of you, but just to keep things going and to set the stage. And then we'll talk about multiple equations, which is the most interesting thing. And then the heart of the talk is the introduction of these fixed point games. So how can you characterize the solution of a system of fixed point equations over more or less general lattice via game? And then I'll say something about soundness and completeness of the game and under which condition this holds, and then we'll conclude. Okay, so let's start with the really easy case. Just to get going, and we're interested, I said, of solving systems of fixed point equations, or now just a fixed point equation, over a complete lattice. So assume you're given a fixed point equation, so the equations of the form x equals fx, and there's an additional index eta, and this eta is either mu or nu, telling us whether we want to consider the least or the greatest fixed point. And f, as usual, is a monotone function over a complete lattice. And just for the terminology, the solution of E is denoted by sol of E. And of course, you all know that there are many, many applications for fixed points in concurrency theory, model checking, and program analysis. And if you look very closely, you basically see fixed points and fixed point equations almost everywhere. So then, of course, we use the well-known Knaster-Tarski theorem that guarantees existence of solutions, so existence of least and greatest fixed points for monotone functions. And actually, a few years ago, I thought, okay, when I want to do fixed point theory, I should know Knaster-Tarski and maybe Banach fixed point theorems and clean iteration, and that's it. But actually, now I think that there's also still a lot of interesting theory here to be discovered. Then how do you compute the least or greatest fixed point? So whenever you happen to have a continuous function for least fixed point or a co-continuous function for greatest fixed point, you just do the following. You compute the solution by clean iteration. So you have this directed chain starting from the bottom element. You do the fixed point iteration. You take the sup. You have the least fixed point. Then if you do not actually necessarily want to compute your fixed point, but you just want to check whether some lattice element is below the solution, well, for the least fixed point, actually Bernhard already mentioned this yesterday, there is actually not such a good notion of a witness that actually proves that you are below the least fixed point. I mean, this is also a problem I'm really interested in. We've done something in that direction, but it's not really the topic of this talk. But you can do some kind of ranking functions as they're used for termination analysis, or you can just do fixed point iteration and check whether after I steps you're above this element. But okay, if you only converge to the least fixed point, that does not necessarily work. So I think there's actually still a bit to be done here to have a witness for checking that you're below the least fixed point. Checking whether you're below the greatest fixed point is often much easier. You just construct a postfixed point, so some lattice element L prime that satisfies that L prime is smaller or equal than f of L prime, and you check that L is smaller or equal than L prime. Okay, so I mean, basically this is the picture that is given to us by the Knaster-Tarski theorem. it says, okay, this whole oval thing here is the lattice with the top element and the bottom element. And in the middle, there are the fixed points, the set of all fixed points for your given function. And below here, you have the post-fixed points. So the post-fixed points are those lattice elements that when I apply the function, I get something that is larger or equal than the previous element. And on top, there are the prefix points, for which you have exactly the opposite inequality. And then you can do clean iteration if your function happens to be continuous or co-continuous. So you start from top or from bottom, and you iterate, and then you converge to the least or the greatest fixed point. And if your function is not co-continuous, well, you might have to iterate over the ordinals. You take your soup, you realize that you do not have yet found the least fixed point, and then you go to omega plus 1, and you keep going with your fixed point iteration until at some point then you reach the fixed point. So the function that I'll consider in the future are not necessarily continuous or co-continuous, but because of this game view that we have, it's not actually a problem. So just some examples of data flow analysis. You're both interested in least or greatest fixed point. Then I'm coming from concurrency theory, where you're often interested in computing bisimilarity, which is characterized as a greatest fixed point. Behavioral metric is actually very similar, just because the order is reversed. So the behavioral matrix that you consider, so behavioral distances, can be characterized as least fixed points. And actually, this is also one of the things I'm really interested in, computing behavioral metrics. But because then the lattice is infinite, and then it's not so easy to actually compute these metrics. Okay, now let's turn to systems of fixed point equations. So assume we have a complete lattice. And now we're giving a system of equations. So we not have one equation, but a system of equations. And in order to give this, we have functions. So the functions are m-ary, so they go from L to the m to L. And we have m such functions. And now we have a whole system of fixed point equations. So you have like x1 equals this. And for each equation, you can change the index. For each equation, you can decide separately whether you want to take a least or a greatest fixed point. So then you get nested fixed point equations. And actually, maybe some of you know this better from mu calculus terms. In mu calculus terms, just basically another representation of this type of fixed point equation systems. I mean, here this is more general in that we take arbitrary functions and almost arbitrary complete lattices. But you can also write this down as more as a term, so like nested fixed points as you would have in mu calculus. And then how do you determine the solution of such a system of equations? Well, you do it inductively as follows. So you kind of assume you already know how to solve a system consisting of m-1 equations. How do you solve a system consisting of m equations? Well, the simplest case is, of course, if you have a system consisting of 0 equations, it's just the solution is just the empty tuple. So the solution is supposed to be an m tuple of lattice elements. And then basically the recursion equation is as follows. So you want to solve a system of m fixed point equations. So what you do, I'm using this notation, this E, where xm is assigned to Sm, basically means you fix the last variable xm and set it to some fixed element. In this case, this element is Sm. And you forget about the last equation. So then you have a system of only m-1 equations over m-1 variables. Then recursively, you solve this system. And then you give back the solution. But how do you get the Sm? So the Sm you get as follows. So basically, you fix this last variable, and you'd call it x. You forget about the last equation, just as before. And then to this solution, which is then an m-1 tuple, you take an addition x. And then you have m arguments. To this, you apply fm. And then you take a function in this argument x, and over this function you take either the least or greatest fixed point, depending on what this index tells you, and then this is the solution of the entire fixed point system. So if you know this evaluation of nested fixed points from mu calculus is basically the same thing. So just to recap, so this means you take a system of m-1 equations that one obtains by fixing the value of xm as x and remove the last equation. Then we fix this value, we solve the remaining equation system parametrized over x, and then we perform a last fixed point iteration on the last fixed point equation. And actually, the order of the equation matters very much. So if you exchange the order of equations, you usually get a completely different solution. And usually, I mean, the last equation is the one that matters and that kind of dominates the other. So the last equation corresponds to the outermost fixed point in mu calculus. Okay, and then the solution is a fixed point of this fixed point equation system, but one of many. I mean, there are other fixed points, but you want this specifically. I've also been trying to kind of characterize this fixed point as the fixed point in the set of all fixed points that satisfies certain properties. But actually, that seems kind of difficult. So if somebody knows how to do this, I would be happy to talk about this. Okay, so let's maybe look at mu calculus model checking and see what it has, how this is related. So I'll talk about the modal mu calculus. And so there are the two operators. And first there's the box operators. And you apply these operators to sets of states. And so the box operators, a state satisfies this box operator applied to a set of states if all successors satisfy the predicate given by the set of states. And we have also the diamond operator, and that says that some successor satisfies this predicate, or some successor is in this set. And of course, then we have least and greatest fixed points and just the usual Boolean operations. And assume that we're giving this formula, and it consists of two nested fixed points. So the outermost fixed point, which corresponds to the last equation, is the greatest fixed point, and the innermost fixed point, which corresponds to the first equation, is a least fixed point. And then these formulas are awfully difficult to read, so I still have a lot of problems doing this, although now I've worked on this for a while. I remember once going to a tutorial of Julian Bradfield many years ago where he explained how to read these formulas. But okay, I'll try to parse them on the next slide. So let's look at this as equations. So in the following, I'll only talk about equations. And so we have these two equations. So this equation here, the uppermost one is corresponding to this inner fixed point from here to here, and this is corresponding to this outermost fixed point. So what does it mean? I mean, it's actually not so important for the rest of the talk, but it's still nice to know what it means. So let's first try to parse the innermost equation. And it's a least fixed point. So basically, it's a kind of reachability property. And here the question is whether there exists a path. So this is basically comes from this diamond and this x1, such that eventually, so least fixed point, so eventually this has to hold, so that P holds, and for some successor, x2 holds. But what is x2? x2 says this is the largest set because it's the greatest fixed point, such that x1 holds for all elements in the set, and all successors satisfy x2. So again, x2 refers to x1, and x1 refers to x2, and this is why they're kind of interlinked, these two fixed points. So if you combine both things, you can figure out that it means that from all reachable states, there is a path along which P holds infinitely often. So you always have to, whatever you can reach, you're guaranteed that there is a path along which P holds infinitely often. And that's actually the interpretation of x2, which is the last equation. Okay, now let's just recap the state of the art in mu calculus model checking. So very often, and that's also the approach that I will be taking, you take one of these mu calculus formula and you transform it into a parity game. And then for the parity game, it's somehow more straightforward to check whether actually a state satisfies a certain formula, to do the model checking. So now assume that n is the number of states and d is the alternation depth of the formula. So alternation of least and greatest fixed points. What you can do to compute this, I mean, now if you look at this from a lattice theoretic point of view, you're working on the Powershell lattice of states. And of course, your functions are of a very special type because they correspond to what you can do with the logic. And you can, okay, so let's say it's a finite set of states. You just do the naive approach and you use the definition, plug in the definition. But that means because of this nature, you basically have to evaluate these equation systems many times. I mean, you have to have many calls, and in the end, you have a complexity of n to the d. Or you can reduce model checking to a parity game, as I already said, and then determine whether the existential player has a winning strategy. And then there are several variants what you can do. I mean, there are these local on-the-fly algorithms that basically construct this parity game on the fly and search for a winning strategy of the existential player. They're not really known for very good complexity, but often since they have this lazy on-the-fly approach, they can be quite efficient. Then there was an approach using so-called progress measures by Jurczynski that kind of halved this exponent. That was already big progress. And then very recently, a few years ago, you get these quasi-polynomial algorithms. That's now the big thing in parity games, because actually now you reduce the complexity to quasi-polynomial. And determining the complexity of parity games is a big issue. So this has now been they made a major breakthrough there. And there have been other approaches that also achieve this quasi-polynomial time bounds. I'm not really be talking about complexity, but okay, the results I'm presenting actually then can also be used to derive complexity bounds, and I'll say something about this at the very end. Okay, so now, okay, this is all if you take the Powershell lattice of states. But one is also interested in taking other lattices. In particular, when it comes to mu calculus model checking, what about lattice-valued mu calculi? So instead of saying that a state satisfies a formula, you rather say your formula is a mapping from X to some set L, where L could be, for instance, an interval in the reals. And then this formula tells you to what degree this formula is satisfied. This is, for instance, what is done often in connection with these behavioral metrics, about which I talked at the beginning. Then instead of having a classical logic that just tells you yes or no, the state satisfies the formula or no. Instead, you get a number, and this is somehow the degree to which the state satisfies the formula. And there are many examples for this. For instance, lattice mu calculus by Kupferman and Lustig, and quantitative probabilistic mu calculus, and Lukasiewicz mu calculus by Miho and Simpson. And in both these cases, you work the lattice is the interval 0, 1. So, I mean, if you want to check these, then of course, maybe the question is, can we do somehow a similar trick? We start with a formula system of equations. You go to a parity game, and then we solve this parity game. Of course, the parity game will be on an infinite state space, so maybe it's not so easy to actually use this. But still, the question is there a game also in this case? And so in any case, what we're interested in, not just to restrict to Powershell lattices, which are the ones, of course, heavily studied for mu calculus, but go to more general lattices. Okay, so now let's slowly come to the game. So we're now interested in more general lattices. I mean, I will make a restriction on lattices, and in the end, it's not all complete lattices. But for now, let's try with just with a general complete lattice. So E is the system of M equations over lattice L, and we fix a basis. So what is the basis of a lattice? It's just a subset of the lattice, such that every lattice element can be obtained as a soup of some elements. General soup, not necessarily directed. And so what are the roles in the game? First, there is the existential player, which we call Eve. And what does Eve want to do? She, given a basis element of the basis, she wants to show that this basis element is smaller or equal than SI. What is SI? SI is the ith element of the solution. So assume that we have a system of equations, and so the system of equation is associated with a solution table S1 to Sm, and we want to check that this is below the ith component of the solution. And then there's the universal player, Adam, the adversary of Eve, and he wants to show that this is not the case, so that B is not below the ith element of the solution. And so actually, of course, what we did, it is based on predecessor games. So of course, parity games was a big motivation. But there's actually, we also based this a lot on the unfolding games by Venema. But those are played on Powershell lattices, and actually, as far as the version that we know, is only for single fixed point equations. So we generalized this to both more general lattices and nested fixed point equations. So we do the first version, which actually has a bit of a problem that we will see later, but for now we will do this. And we start with Bi, and this means, so now we want to show that the B, the element of the basis, is below the ith components of the solution, and it's Eve's turn. So Eve's turn, and what does she have to do? She has to provide us with a tuple of lattice elements such that applying Fi to this tuple, you're above B in the lattice order. And then, okay, given this tuple, it's the term of Adam. And what does Adam do? He chooses one of these components, J, and an element B prime, which is a basis element, which is below Lj, so the jth component. And he challenges Eve and says, okay, please now tell me how to cover this with the function. So the basis element should not be, the basis element should not be bottom, because if for all takes bottom, for all Adam has lost. And what are the winning conditions? So these should look familiar for people who know parity games. So of course, if one player is unable to move, then the other player wins. But otherwise, if it's an infinite game, you take the highest equation index that occurs infinitely often. And if this is a nu index, then Eve wins. And if it is a mu index, then Adam wins. So this is the parity condition, actually. Okay. So basically, this means that the outermost fixed point that is visited infinitely many times, that's kind of the most important one, and it dominates all the others. Okay, so now actually, I wanted to play a bit with you, but let's first explain what we have to do. So actually, let's do this mu calculus example. It's just Powershell lattice, but I think it's maybe easy to figure out what this game is about. And actually, the game that you get is just a parity game, but the construction is slightly different than the one that is given in the literature for the mu calculus. But in the end, you get more or less the same thing. So the Powershell lattice is the Powershell lattice of AB. So these are the two states. This is exactly the formula of the equation system that we looked at before. So remember the x2. So the solution for x2 is all reachable states such that there's a path along, from all reachable states, there's a path along which P holds infinitely often. And actually, this holds for all reachable states, because here P does hold infinitely often all the time, and from here you can always reach this state from which P holds infinitely often. So both states satisfy this. Okay, so these are the two equations. So now I'll do a tiny bit on the blackboard. So sorry for all the zoomers, because this might not be very readable, but then I'll come back to the slides very quickly. So let me see. Okay. So I can draw this as a parity game, and basically, so we start with a state of the existential player. And the state of the existential player is that the existential player, so that is Eve in this case, wants to show that state A satisfies the property, and that state A satisfies the property. I want to show that this set A is below the second component of the solution. And then what is the aim of Eve? So the aim of Eve is to substitute something into the second function, which is f2. So I want an x1 and an x2, such that A is below this here. So what do we have to substitute here? So basically, I mean, for A to be in here, x1 must contain A. And actually, I want to do just the minimal possible moves, because Eve never wants to do a move that is too large, because Eve is always better off with a minimal move. So she chooses A here. And here we also have to get a set that contains A. But in order to contain A, we must here give all the states, because A has successors A and B. And then if you put the set AB here, then A will be contained there, because all successors of A are in this set. And if it's a smaller set, A will not be here. So we have A and AB, and then Eve should play this. And we go to a position of Adam. And what does Adam do? He chooses one of the basis elements, either basis element below here or a basis element below AB. If he chooses this A in the second component, it just goes back. So it's A in the second component. If he chooses B, you get here B in the second component. Or you can also choose A in the first component. And then again, we're at the node of Eve, and it's Eve's turn then to do something. OK, and then of course this is slightly larger. So I already explained the game positions. So diamonds for the existential player. Now I should switch off the light. And boxes for the universal player. And this is the game. And we start here. And since actually the formula is satisfied, the existential player has a winning strategy. So I would say that you are the existential player. I think the people on Zoom can also play if Uli tells me about the moves of the. So you are all the existential player, meaning you move at the diamond nodes. And remember, so I mean, there are no finite games. So you should make sure that the highest index that is visited infinitely often is a new index. And 1 is a mu index, and 2 is a new index. So you have to visit the 2 infinitely. Make sure that you visit the 2 infinitely often. So it's your turn. We start here. You're the existential player. You have to do something. Well, in this case, we just agree that you're here, that we're here. OK, so then it's my turn, and I go here, so to A1. So we're now on the leftmost diamond node. Now you actually have a choice. What do you do? You turn right. OK, you go here to B empty set. So this is the middle square node on this intermediate level. So we're here. OK, so it's my turn now. Now I don't have much of a choice. So I go to the lower diamond node to B1. OK, let me remember what we've seen so far. As parities, we've seen 2, 1, 1. You want even number to occur infinitely often, the 2, 2, 1, 1. So you still have a bit of work to do. Now you're here. Now what you do now? You go in this way, OK, to the right. OK, that's a good choice. Actually, you have 2 possibilities, but you go to the right to empty set B. And OK, now I only have one choice. I go up here, and we saw another 2, which is good for you. OK, so now here, we don't have a choice. You go here. Now I could go back here But of course, then this would mean that we can just repeat this cycle, and then we will have seen the 2 infinitely often. So maybe to make things a bit more interesting, I go here, and you go through the right again. Okay, and then we'll basically cycle here on this rightmost cycle, and we will see the 2 infinitely often. And this is something I cannot avoid, and you will win the game. Okay, so and this is actually the strategy that you should follow, and you did. Okay, so now of course we come to the new stuff, more interesting stuff. So is this game actually correct and complete for all lattices? So I just gave you the game without that much explanation. But of course we want the theorem that says that if has a winning strategy for position bi if b is below the ith component of the solution. And this is actually wrong. So I mean, basically I gave you a game that was wrong, but of course it can be fixed. And so for instance, in a lattice where it doesn't work, you take the natural numbers, including infinity. So here on the right-hand side, you have this lattice with infinity on top. And this function is just the function, the increment, and if you increment omega, it's just omega. And then if you in order to play a game, check whether omega is below the solution, and omega is below the solution because you take a least fixed point equation, and the least fixed point is omega. It's also the greatest fixed point, but here then the existential player has to provide omega because she needs a value set that if you apply f, you're above the solution. So this is only true for omega. And then the for all player just chooses something that is below, but the for all player can also choose omega, can do Adam, and so this goes on. And for all, we'd win the game because it's infinite, and the highest index that you see infinitely often is a mu index, an index of a least fixed point equation. So this game is actually, in the generality that I told you, is wrong. So let's analyze why it is wrong and explain which additional condition I need so that it becomes correct. So what is the problem here? The problem is that omega is below the least fixed point, so it is below this sup, but it is not below any of the components in this directed chain, which means that somehow the existential player cannot go down in this chain. But in order to win, if you think about this also in terms of ordinal, if has to go down the chain of ordinals in order to at some point reach the least ordinal to win. I mean, if you have just the least fixed point equation. And so Eve should be able to enforce a finite game. So she has to be able to go below the limit ordinals, basically, in the fixed point iteration. But the solution is if you restrict the basis to be, okay, this is a bit nonsense. No, this is okay. That the basis is just the natural numbers. You have to omit the 0 because the 0 is bottom, it is included. Especially you exclude omega from the basis. Then actually this forces Adam to pick a natural number instead of omega. And then Eve can win because then she can really go down the chain and pick smaller and smaller elements. But of course, this is just for this specific game. So what are, in general, the restrictions on the basis? And for this, we need the notion of the so-called way below relation. And so first I'll define the way below relation. And assume you have two elements, L and L prime of your lattice. And you say that L is way below L prime when the following holds, when you have a directed set D, and the sup of this directed D covers L prime, so the potentially larger element of the two, then you are guaranteed that there is an element in this directed set that L is below this element. This is the so-called way below relation. And for instance, in the example we just had, omega is not way below omega, since omega is below the sup of all natural numbers, but omega is not below any element of this directed set. And we can also look at other lattices. For instance, Powershell lattices. A set is below another set if it is included in that set and the y is finite. And in the reals, the way below relation is the strictly smaller relation, apart if x is 0. So x is 0 is way below everything else. Okay, then we'll come to the notion of algebraic lattices. So we give some restrictions for which the game works. So an element is compact, this is the terminology there, if it is way below itself. For instance, the natural numbers are way below themselves, but omega is not way below itself. And a complete lattice is algebraic if the compact elements form a basis. So basically, if everything can be generated from compact elements. Every Powershell lattice is algebraic. Also, the natural numbers with omega is algebraic. But 0, 1 is not algebraic because the 0 is the only compact element, and that is not enough to generate everything. Okay, now we come to the first result for the first version of the Fixpoint game. Actually, this game is always correct in the sense that if Eve has a winning strategy, then we're below the solution. But it's complete, so the other implication holds if and only if, so this is really an if and only if the basis consists of compact elements. And if we have a basis of compact elements, the lattice must be algebraic. And otherwise, if this is not the case, we can construct a function and a game so that actually the completeness does not hold. Okay, that's nice, but then of course algebraic lattices are a bit restricted. I mean, in particular, since we always have these application examples in mind, like behavioral metrics, but also just things like termination probabilities or whatever, you really want to include this lattice also. So what do we do to have this as well? And the idea is to switch to continuous lattices. So continuous lattices were introduced by Scott for semantics of the lambda calculus. I wondered for a long time why they're called continuous. I still do not really know, actually. Scott says in his paper, I call this lattice continuous because it allows so many continuous functions. I mean, maybe particularly the meat is continuous in this setting. So the meat distributes over directed soups. So, but what is a complete lattice? So a lattice is continuous if for all lattice elements it holds that L is equal to the soup of all elements that are way below it. Now the 0, 1 is a continuous lattice because every real number is the soup of those real numbers that are strictly less than this number. Algebraic lattices, of course, are also all continuous. That follows from the definition. And here is a lattice that is not continuous. Why is it not continuous? The point is mainly that A is not way below itself. Why? Because you can cover A with this chain, with the chain of the, not including omega, the chain of the real numbers, the soup of the real the natural numbers. But A is not below any of these. So this is a non-continuous lattice. But you really have to look a bit for non-continuous lattices. And then there's a second version of the Fixpoint game that is exactly the same as the old one, but only here in this position you replace smaller or equal by way below. And otherwise it's unchanged, and also the winning condition is unchanged, and it's the same thing. Okay, and now you can think whether this game as we have it now is sound and complete, this Fixpoint game of this second version. And actually, and now it's a bit the other way around. So this is always complete. And it is correct if and only if the lattice is continuous. So one can show. I mean, the proof is a bit involved. I mean, we were using many ideas from parity games that basically show that encoding mu calculus into parity games it gives you the right notion. I mean, that's also maybe not always that obvious that mu calculus term can be encoded into a parity game, and then the winning strategies there tell you exactly which states satisfy the mu calculus formula. So the proof relies on ideas there, but it is kind of, you have to do quite some work to show this result. Okay. So now at this point, and it's also we were at this point, we were like, come on, this game, why does this game actually hold for the reals? I mean, this was something that really surprised us, and actually at first we thought we cannot just get a game for this case, because you would think that when you do the game you kind of converge to something, but somehow you really have to show that you're really going down the chain of the ordinals, for instance in the case of a least fixed point equation, and you reach 0 at some point. And in order to show that, I mean, that's not a proof, of course, I mean, to really check the proof works, but just kind of to convince you that things work fine, in particular for non-continuous functions. Maybe for continuous functions you think, okay, why not? It will probably work. But why does this work for non-continuous functions? And just to give you a bit of an idea, here's a non-continuous function, and we want to check then in the end that we're below the least fixed point of this non-continuous function. And so this is this piecewise linear function, and it makes a jump here at 1/2. Sorry, this is automatically generated, so it's 2/4, it should be 1/2. And so until there it's this linear function, and then it's this linear function. And the least fixed point is here, where this intersects with the diagonal. So the least fixed point is 3/4. It's also the only fixed point. And it's not reachable in omega steps, since the function is not continuous. So you would have to, you have to fixed point iteration here, then you end up here after omega steps, but then you're not yet done. You apply the function, you end up here, and then you have to continue fixed point iteration a bit, and then after omega times 2 steps, in the end you're here at the fixed. But why does the game work? So the game works more or less because you start with 3/4, and you want to show that 3/4 is below the least fixed point. So the existential player actually has no chance then to answer with 3/4. But now the atom, the universal player, has to pick something that is way below 3/4. And way below in the reals means strictly smaller. So so Adam has to commit to removing some small epsilon. Could be very small, but just a small bit is okay. Which means then that is because of this factor 1/2 here, that then the existential player can then choose 3/4 minus 2 epsilon. Then suddenly you have a handle of really going down. So then this goes on for a while until at some point we reach this point here, which is 5/8. And then the existential player can choose 1/2, so this one, because it covers 5/8. And then again, more or less in the same way, Adam is forced to subtract something, and then you go further down this chain until at some point you reach 0. But 0 is not in the basis by definition, and that means that the existential player wins. I mean, because here the universal player would have to pick 0. So actually that also works, and which at least to us it was a bit surprising at first that it does work also for non-continuous functions. Okay, so I'll come to the conclusion, but I have a couple of slides here. So first I want to tell you about those things that I did not talk about in this talk. So I debated with myself whether I should also talk about progress measures. So progress measures are basically, it's a way of compute the strategy of the existential player. It's a global algorithm, not a local algorithm that checks only for a specific game position, whether the existential player has a winning strategy. And basically, it gives to every game position a vector of ordinals. And the vector of ordinals tells you when you've last seen a game position with this specific index. And once you see a greater index, you have some resets. So they actually work with a lexicographical order on these vectors of ordinals. And this is basically also one of the algorithms. This is the algorithm proposed by Jurczynski, with you can solve parity games. And of course, in this case, just assume your state space is finite, then you do not actually work with ordinals, but just with natural numbers up to some bound. And this works here. I mean, you have to go to the ordinals, of course, for general lattices. And so there's a global algorithm for computing these progress measures. There was also a paper by Hazuo et al. Earlier that also already used this idea of working with progress measures for these generalized fixed point equations, and we coupled this with a game and then gave a specific recipe based on the game how to compute these progress measures. Then actually we fixed one problem that you get, and the problem is a bit that the existential player usually has a lot of options. I mean, here I already told you, let's take only the minimal options of the existential player, but instead of taking A here in this first position, I could have also taken AB. But in some sense, the existential player will never do this, because for the existential player, it's better to constrain the move of the universal player and to pick as little as possible. So the idea is, in order to be somehow more efficient, get more efficient checking algorithms, we constrain the moves of the existential player via something that is called selections. And then based on these selections, at least in the case of finite lattices, you can automatically infer fixed point equations for computing the progress measure. So in the end, the progress measure is also computed via a fixed point equation. And then you can efficiently actually compute the winning strategies for the existential player. Not so much, of course, if the lattice is infinite. Then the question is, of course, I mean, then the game works. But of course, the next question is, does this game help me in any way? Because in the end, I'm interested in computing the fixed points, or maybe not computing the fixed points, but deciding whether you're below the ith component of the solution and have some decision procedure. And of course, this is not so clear for the infinite case. And then we wrote another paper where we described a local algorithm for checking whether lattice element is below the solution. So an on-the-fly algorithm that just unfolds the parts of the game arena that are actually necessary. There's also, we integrated this with up-to techniques and actually Galois connections for abstracting and concretizing the lattice. And so combined with these up-to techniques, actually you have mechanisms also for stopping earlier. And you do not have to unfold the whole game arena. And from this, you actually also get a variant of the game that in fact works on all complete lattices. There's only a drawback because instead of playing on the basis, you play on a power set of the basis, which is somehow gives you more moves than maybe you would like to have. Okay, then at the beginning I said something about these complexity results. So there are these new quasi-polynomial algorithms for mood calculus or parity games. And yes, these are now very much en vogue. So lots of people are studying this. And of course, the question still remains if you can also do it in polynomial time. This is an unknown question, whether you can solve parity games in polynomial time. But at least now you have these quasi-polynomial algorithms. And then, of course, the question that kind of arises from our game, because we generalize the parity games, can you now also get quasi-polynomial algorithms for arbitrary lattices? Well, maybe not arbitrary lattices, because for infinite lattices, certainly you have to do other stuff. But for finite lattices, and this is something that we did not do, but there's a recent paper by Daniel Hausmann and Lutz Schröder, who then did quasi-polynomial computation for nested fixed points, also based on our game, that then gives you this quasi-polynomial algorithm. Of course, there's a couple of open questions, and what I would really like to do is to use the theory here to actually help compute solutions of fixed point equations over first just fixed point equations over the reals, but in the end, one thing I'm really interested in computing fixed point equations over behavioral metrics, maybe just one fixed point equations for a start. and maybe also other infinite lattices. And so in order to do this, we did some initial experiments with SMT solvers. So we set up formulas that characterized whether Eve has a winning strategy, first order formulas. And we put them into SMT solvers, and then the SMT solver, if there's a solution, if the formula is satisfiable, you get a winning strategy or not. This kind of works, but I have to admit it doesn't actually scale very well. And so the question is a bit still open, whether this game can also help for doing something with infinite lattices. So currently we're working on methods for approximating the solution. So assume you're given a Fixpoint equation system, and you don't actually want to compute the solution, just have a way of approximating it. Actually, this turns out to be very complicated. And the problem with that is, assume we start just with continuous functions. All the fi functions that we have are continuous. But then the problem is that once you start taking fixed points, your continuous or co-continuous functions will become non-continuous. And then in the next iteration, suddenly you have to deal with a non-continuous function, and then you cannot just simply approximate your solution. That's amazingly complicated. But okay, we have some initial results there. But still, I mean, I think there's quite a few open questions here, and I think there's still quite a few things that you can do there. Okay, so maybe I'll stop here, and thank you very much for your attention.
Are there questions?
Yeah, thanks for the very nice talk. I have two questions, and I'm afraid the first one is a silly one, but in this game under real numbers, for the non-continuous function, you said that eventually you will reach the zero. Mm-hmm. But why do you reach the zero? I mean, is it the existential player who chooses the zero, or the...
Okay, it depends a bit. I mean, either it is the, I mean, of course you go down. You basically go down because the universal player has to choose this delta. And now I'm not completely sure. I think both could reach the zero. I mean, the existential player can always give an element such that you are larger. But I mean, at some point, basically, when you reach this, then the only way that universal player can answer is with the zero. I mean, the existential player, if the existential player would, reach the zero, also the existential player answers with a general lattice element. So the existential player can take zero if necessary. But then the existential player, okay, sorry, maybe I should say this better. So at some point, then the existential player can take the zero, which is okay. So because at some point 0 then covers this 1/4, and the existential player can take the 0 because it's just an arbitrary lattice element. And then the universal player would have to take something that is way below. Actually, 0 is way below itself, but the 0 is specifically excluded. Yeah. And we would not have to exclude it if directed sets could be empty, because then actually 0 would not be way below itself, but directed sets must be non-empty, so we have to. So this is the reason why we have to make this case distinction here.
I think I was missing that it starts at not at 0 but at 1/4 on the y-axis. I think that was what I was missing.
Yeah, that's the value that you reach here, and then at some point.
So the other question is, you have like continuous lattices but non-continuous functions.
Yeah.
But I mean, it would also work the other way around, wouldn't it? If you have any lattice but a continuous function, because then you cannot have this omega problem that you have described. Because then at omega you're already at a fixed point if the function is continuous.
Okay, this is a good question. So actually, I think that maybe continuous lattice and continuous functions do not have so much to do with each other. Whether it also works the other way around. I actually don't know. We didn't think about it. I'm a bit skeptical because Now we're trying to solve this for a case where we just have continuous functions, and the problem is they break or stop being continuous after taking a fixed point. So I'm a bit afraid that you will run into a similar problem there with nested fixed point equations, but I'm actually not sure. I don't know.
Yeah, might be. I mean, I think one of the problems will not be there, but maybe there are other problems then.
Yes.
Yeah.
Yeah.
Okay, thank you.
I didn't. Okay.
Yeah, thank you, Barbara. Okay, while we are here, I have another question actually. So can you characterize precisely for which non-continuous functions those things work? Just in this case of
for non-continuous functions?
Yeah, for which ones does it work and for which ones doesn't?
Well, assume that now we have 0, 1, which is a continuous lattice. We can do all non-continuous functions, as long as they're monotone, of course. I mean, they must be monotone.
You need monotonicity, obviously. Yeah, okay,
yeah.
okay, but okay, thank you.
Yeah.
Okay, second question. How are your fixed point games related to co-density games?
The co-density games. So as far as I understand, co-density games, they are for behavioral metrics.
Yep, exactly.
And so they check, they're for checking whether, I mean, basically the idea is you have a transition system, you have two states, and you want to check whether the distance of two states is bounded by some constant. And then the codensity comes from the codensity lifting, which is a specific functor lifting, which is, let's say, Kantorovich lifting, more or less, in the probabilistic case. And then you play the game there in order to check this. So I mean, usually they take a least fixed point, so it's a least fixed point game. And actually, I think, of course, it's also least fixed point equation, so we could also do this game. But what we will get is probably a slightly different type of game, because the game that they get is more or less like the bisimulation game. And of course, you could also do bisimulation games here, but instead of the standard bisimulation game, you get a game where not one player makes a move and the other answers, but one player, basically the existential player, it takes a coupling of the successors, and then the universal player picks one state, and you go on from here. And I think here we would probably more get this coupling game, but the codensity game, if I remember it correctly, is not such a coupling game. It's a slightly different type. So, I mean, in the end, it's a game that do the same thing, but I think the rules will be slightly different.
Maybe a stupid question, maybe I missed some. In these strategies, so in the finite case, could they be always made computable for Eve, for example?
Yeah. In the finite case, you can compute the strategies, because then you can do this, you can compute these progress measures, and then basically the progress measure is characterized by a fixed point computation on a finite domain, and then you can compute the fixed point. And then you know the strategy. Yeah, you can then decide things as for mu calculus.
Okay, thank you.
But not in the infinite case. That's our problem.
Barbara, can you please recall briefly what are behavioral strategies and how they form a lattice, and what kind of lattice? Is it continuous, algebraic, these kind of things?
Behavioral strategies?
Behavioral metrics.
Behavioral metrics. Behavioral metrics are basically you just have a lattice of metrics or pseudo metrics. I mean, the behavioral comes more from the fixed point equation, because it's because it's based on some probabilistic or metric or whatever transition system. So the lattice that you use is just pseudo matrix. So functions from, should I maybe write this here? So it's just functions from x times x is a some set to 0, 1 that are pseudo matrix. So so the distance of x is 0, your triangle inequality holds, symmetry holds, and this is a lattice, not distributive, but it is a lattice. And then this is also continuous because basically this is continuous. And yes, and then you can have to define your fixed point functions on this. So lots of people are now using this behavioral matrix as a kind of a replacement for behavioral equivalences. I mean, instead of showing that two states are equivalent or not equivalent, you say these two states are equivalent, but okay, or that their distance is some kind of epsilon there, so they are close or not that close.
Okay, that's probably a good place to stop. Thank you again.